Thank you, Roberto. Thank you to the organizers for the opportunity to speak here. So I guess when I started working on quantum field theory, my motivation, and probably was similar to the motivation of everybody else, just to understand nature at a fundamental level. This is what quantum field theory was about, and nobody would be worried that it might get used for something. Okay, times have changed, and now there is a serious risk that quantum field theory might actually get used for something in terms of quantum information. And now, of course, there is a large field of relativistic quantum information theory. But this talk is somewhat motivated by questions coming up from that direction. But it's a little bit of a motivation, and one could have had these questions all the way along when studying quantum field theory without worrying about what it might actually be used for. So here are some fundamental issues. Some of them are very old, some of them are more recent in some ways. What might we want to do if we are thinking about measuring or using a quantum field theory in some sort of information context? Well, we need to be able to transfer information, okay, from one quantum field theory to another one. We need to get access to observables. And not just talk about observables and say, there is an observable in some algebra, but we may wish to get access to it, to get information about it. And, well, we might be happy to do that approximately, but ideally we want to do it exactly rather than approximately. We also, if we're setting up some sort of measurement or setting up a device for measurement and so on, we need to be able to prepare the quantum field theory in a given state. And we don't necessarily care about doing that for the whole universe. The rest of the universe can look after itself. But what we really care about is doing it locally in the device that we have in front of us, or in the region of space-time that we want to control. But importantly, we're nice people. We're not selfish. Okay, we want to prepare something, but we want to allow other people to prepare things as well, provided they're a little bit away at space-like separation. Okay? If they're over there, then that's fine. They can do what they want. They should be able to do what they want at space-like separation, because we should not know of each other's presence whatsoever. All right? So there should be no obstruction to each of us doing what we want with the quantum field theory. And we want to know how to update states after we make a measurement or do some operation on the quantum field theory. So what I'm going to do in this talk is try to explain how all of these things can be done in a way that's local and covariant, working in flat and curved space-time. And this is all within a framework that Rainer Fesch and I, this is very odd. I think it's, yeah, okay. A framework that Rainer Fesch and I developed about 5 years ago or so. Okay, so here is a rough outline of that framework. We are going to have what we call a system. That's going to be modeled by a quantum field theory, an algebraic quantum field theory, and it's going to live on a curved space-time M, which we require to be globally hyperbolic. And that will be called A. Ooh, I really haven't got the hang of. Yes, there we go. That will be called A. And we also have a probe, okay, that we're going to use to interact with this system and make measurements about it. That will be called B. And then we're going to compare a couple of things. I can, of course, put A and B together in a very simple-minded way just by taking a tensor product. And this I call the uncoupled combination, right? Because they each have their dynamics and there's no interference between them. But I also consider another quantum field theory that will be called C. And this is the coupled combination. And it's a quantum field theory in its own right. And it will agree with the uncoupled combination outside some defined region of space-time. And that defined region of space-time will be called the coupling region, K. And the only thing we assume is that A and B are quantum field theories, QFTs, and so is C. And there is this coupling which is localized in space-time. And then I'm going to show you this on the next slide, but if we combine these assumptions with standard QFT and space-time geometry, we realize that there are some isomorphisms, tau plus minus, going from the uncoupled theory to the coupled theory. And these really give you the identifications between the uncoupled and coupled theory at early times, if it's a minus, or late times, if it's a plus. And of course, I can put them together like this, these two isomorphisms, or automorphisms even, and I form what I call a scattering map. And that's going to know about the dynamics. It compares the dynamics of the uncoupled and the coupled theory. So here's how it works. Space-time, here is a nice green space-time, M, and there is the coupling region within it. And I have my uncoupled theory over here. Now, what I can do is I can delete the future region of the coupling region, right, the J plus, and I'm left with another space-time, M minus. And so I know what the theory, the uncoupled combination, should have as its algebra on this M minus region. And likewise, I can delete the past region of K and get a space-time M plus, and I have an algebra here. And I can do the same for the coupled combination over here. Okay, again get algebras for the future region and for the past region. And now I use the time slice axiom and say, well, you know, these regions M plus and minus each contain Cauchy surfaces for the space-time, and therefore there should be an embedding of this algebra for the out and for the in regions that are also isomorphisms. Okay, so I have isomorphisms in these places, and also for the coupled theory, right? And then the last assumption was that there should be no coupling outside the region K. And that means that in the out region, the uncoupled theory and the coupled theory should be the same. So there should be an isomorphism here, and likewise in the in region, there should be an isomorphism there. There is slightly more going on here because these isomorphisms are actually compatible with isotony within the in region and out region, okay? So there's a little bit more going on here than I'm showing. But you can see easily from this diagram that now I can just chain the isomorphisms together, sometimes going against the direction of the arrows, and my Tor plus is just the composition going around the outside, and Tor minus is the one going down at the bottom, and I put them together to get the scattering map, and it's like that. And I get an automorphism of the uncoupled theory. Right? So all of the information about the coupled theory is now residing in this automorphism of the uncoupled theory. And I will use that in what follows.
Can I?
Yes.
So these algebras, you know, assumption, sister algebra from the
No, you
logical.
can do either, right? So you could have just star algebras, or you can do this for von Neumann algebras, right? And then of course with the maps would have to be appropriate.
Okay,
right?
so the assumption works in.
Yes, that's right. So think of them as your favorite sort of algebras and then the corresponding sort of morphisms. Yeah. Okay. So now we can develop what we call the measurement scheme. And so this would be a very typical sort of experiment, or at least as a mathematician imagines an experiment to be. So you have your system and your probe, and you prepare them at early times, right? And you prepare them independently. So what does that mean? It means we choose a state omega for our system and sigma for our probe. And on the uncoupled combination, I know exactly what state I should put. I should just tensor them together. And then this is uncorrelated. So this is how I prepare the uncoupled combination. But of course, the theory, what I've actually got in the lab is the coupled theory. That's where something is actually happening. So I need to translate this description on the uncoupled theory into a suitable state on the coupled one. And because I prepare at early times, I use this Tor minus automorphism. I have to invert it and take the dual, and then I get a state on the coupled theory, which is my best equivalent to the uncoupled state here, the tensor product state on the uncoupled theory. Okay, so that's how I prepare my system. But then at late times, we measure. So we have the coupling at intermediate times. And at late times, I measure something on the probe. So probe observable B. So I now, again, follow a similar pattern. In the uncoupled combination, I know exactly what observable that would correspond to. I just tensor it with the unit on the system. And then I have a corresponding observable in the uncoupled theory. But in the lab, I have the coupled theory. So I need to make another translation. And I do that because I'm making the measurements at late times. I use this Tor plus automorphism to carry it over. And so now I have an observable of the coupled theory, and I have a state of the coupled theory. And I can now ask, what is the expected outcome? And I can, the result, it's a very trivial one, I will show you in just 1 second, is that the expected value of the measurement at late times of this probe observable is the expectation in the system state of a system observable, which I write as epsilon sub sigma of B. And there's an explicit formula, and here we see the probe observable B. There's the scattering map, and this thing, well, it's a conditional expectation, of course, just tracing out the probe using the probe preparation state. Okay, so the proof is absolutely trivial. We just start calculating, and of course we take the dual map over to the other side. It loses its star. Now we see the scattering map, and then finally this is now just the definition of what this eta sigma does. Okay, it sort of takes this partially takes the expectation in sigma. So to every probe observable, there is a corresponding observable of the system, and the expectation values match. Okay, so we can think of the measurement of the probe observable as an indirect measurement of this particular system observable. Okay, and we call it the induced system observable. So there's a nice formula for it. Once you know the scattering map, of course, you just need to plug this in. We use Tor plus and minus to derive that it's the right thing to do. So there are lots of good properties of this measurement scheme relating to locality. So we can ask, where are these observables localized? And you can prove, just assuming Hague duality as well, or a version of Hague duality, that these induced observables may be localized in any open causally convex neighborhood of the coupling region, right? So where they live is around the coupling region. And that's very, very natural thing to say, okay? So when you couple two things together, you don't learn about something over here, you learn about the region where they got coupled together. I highlight protection of ignorance, right? Because there's a lot in physics that we are in principle ignorant of, right? We don't know what's happening in the causal complement. We shouldn't know what happens in the causal complement. Anything that damages that ignorance of the causal complement would be very dangerous, all right? So we need to see that ignorance is protected, and you can do various checks of that, and ignorance is protected in all the right places. Okay, so that's good news. And of course you can say, well, how do you measure your probe observable? Okay, well, of course you couple it to another probe, right? And how do you measure that? Well, you couple it to another probe. You can iterate this whole system, and the mathematics works just the same way, and you can get very sensible things. There are even classes of observables, these so-called Gaussian POVMs, or Gaussian modulated POVMs, that are stable under this process. So if you want to measure a Gaussian POVM on the probe, the induced observable is another Gaussian POVM, and you can see how the parameters change, right? This is Mandrisch and Vasquez. A very important question for an experimentalist might be, how do you solve the inverse problem? Suppose I have a specific observable in the system. Can you design for me a probe, a coupling, a preparation state, and a probe observable that will measure that thing? Okay. There is a point in Hague's book where he says something to the effect of an experimentalist comes to you and says, how can you measure a local observable? And what he actually says is, we don't know and we don't care. Quite a definite statement. Maybe I think I have to check the exact wording, but effectively that's what he says. But that's maybe too defensive. And once you have a model for saying how measurements are taken, you don't have to be as defensive about that, but it's still a hard problem. And that's actually not a surprise, because experimentalists at least tell us that they work very hard on designing experiments. Okay, so that is their job, right? But with physical pieces of kit, to measure a particular thing, you need to know how are you going to do it. And they tell us this is not an easy thing and they need big budgets and things like that. So if we believe them, then it's not surprising that it's a little bit harder to figure out the solution to this inverse problem. Now, in the Mandrich-Vasquez case, it's quite easy because you've got this class that's sort of closed. So you know how the parameters change as you go from probe to system. So you can just invert that and figure out what Gaussian POVM you need. Okay, so that's one class where you can solve it. And then a result of myself and Ian Jubb and Maximilian Rupp is that in a class of free models, then at least in an asymptotic sense, every local observable can be accessed through one of these measurement schemes. So there's a limiting sequence of induced observables giving you what you want. And here, of course, you need some topology to make it work. Okay? But then you can still ask the question, can you do this exactly rather than just in this asymptotic sense? So that's one of the questions that I'm going to answer in this talk. Let's turn to states. Okay, so what's the state for? Well, my claim is it is there to predict expectation values of measurements, okay, observable. And so then when you take that operational viewpoint, what is a state update for? Well, you make a measurement, write it down carefully, and now you want to make further predictions for what happens next. Okay, so the updated state is the state that answers the question of what happens next. Okay, what do I use to predict further experimental outcomes? So this has got to predict expectations for future measurements consequent upon earlier ones and conditioned on their results. And in the Bayes center, this is a very Bayesian process, okay? This is exactly what we use, and it's Bayes' rule. That's what is actually being used in this, in deriving the fact that actually this criterion, in fact, uniquely determines the updated state, okay? So there's no mystery about what the updated state is, okay? And I think that when people learn quantum mechanics, often this is sort of some mysterious process. But actually, what it is all about, this updated state business, is what predicts future experiments conditioned on the results of previous ones. That's what it's for. And once you take that viewpoint, then you know what it is. And here, for example, is the updated state for a non-selective measurement. So there might be a number of outcomes. The experiment is made. We don't know what the outcome was. This is why it's non-selective. Or maybe we do, but we have a big spreadsheet and we don't care which column we're in for the outcome. That's a non-selective measurement. So ignoring the result of what this experiment was, there's a very simple formula. Here we see a future observable whose expectation we want to predict. We tensor it with the unit, we hit it with the scattering map, and then we just evaluate. Here again is the probe preparation state, and there's the original system state. So it's a very simple formula again. And yeah, again, you can start proving theorems about it. And there are lots of good properties of this update rule. There's also a version for selective measurements as well. And one of the properties, one of the things we were able to show was that there is no so-called impossible measurement problem. And maybe I will, if I don't have a slide prepared, maybe not everybody knows this one, say a little bit about what that is. So this is a problem raised a long time ago by Raphael Sorkin. And in outline, he considers three space-time regions, A, B, and C. A is going to be space-like separated from C, but has some overlap with the future of A, and also, of course, overlaps the past of C. And what Sorkin did was he said, well, we're going to imagine a situation where A is making a where B is certainly going to make a non-selective measurement, and A is going to choose whether or not to make a non-selective measurement. The question is, can C tell whether A did or did not make the measurement? They are at space-like separation, so it ought to be impossible for C to tell. And Sorkin wrote down a plausible local measurement update that happens in B and says, aha, C can tell, apparently, whether A measured. Sorkin was not saying, I have discovered superluminal communication, right? He actually said, there is no superluminal communication. This apparently plausible update must be impossible. And then took a further step and said, well, since there didn't seem to be anything particularly special about the example I gave, then it's really now unclear whether you can measure anything, or, because apparently reasonable things go wrong. How on earth do you tell what's going to work? Right? So this problem was around for 30 years. If you do things in this way, and that was another collaboration of
what do you mean by, sorry, non-selective?
non-selective is where, for example, there could be a two-outcome experiment, and you know the experiment is done, but you don't know what the outcome is.
Okay.
Yeah. Or you just ignore what outcome it was. So that's non.
So you don't have a filter, say, but just measure and
Yeah.
it go on.
Yeah, exactly. Yes.
Would each of these observers have a different probe theory?
Yeah, so in the way we resolve it, that's in this paper here, we said that, well, if Alice makes her update using a probe, this non-selective result, and Bob has another probe that he is using to do his non-selective measurement, then you prove that the expectation values that Charlie finds are independent of whether or not Alice actually measured or not. So it comes out very neatly. So this was, as I say, Henning Bostelmann, myself, and our former PhD student, Maximilian Rupp. Okay, a very important thing that Rainer and I prove in our first paper is what happens when you have two experiments at space-like separation, right? So an obvious problem in any relativistic account of measurement is that there is this relativity of simultaneity. So if they're at space-like separation, you can't say this one measured first and then that one, all right? But if you've got an update rule, you face the problem of, do I apply this rule first and then that one, or that one first and then this one, or is it something altogether crazily different? And what we proved, Rainer and I, was that in this update at space-like separation, you can go in either order or all in one go. You can think of it as a single sort of super measurement that's being coordinated by some super user, and you get the same answers. Okay, so this is a consistency check on the whole thing. Sorry?
Use locality.
Yeah, of course. Locality is at the, so I mean the whole point here, right? So the Sorkin thing, the Sorkin's problem is an apparent violation of locality. So the solution is just to say quantum field theory is local. So use quantum field theory, and then everything should work out, and then you check that everything does work out.
Sorry, I have another.
Yeah.
When you have this chain here,
yeah.
So typically when you check probabilities in quantum,
No, keep it.
You need something which is in the future of the first measurement. So the problem is that B is not in the future.
Yeah.
So it's partially on the future.
That's right.
So you cannot use quantum mechanics in a strict sense.
You can. So we're able to say so here we're able to say what is C's, I mean, so the problem would be if you believe that there is some sort of instantaneous collapse rule, right? You have a real problem in working out how that would go here. But here we have clear rules about how to compute C's expectation value if both A and B do this non-selective thing. And if only A does. And you check it and it's the same.
It really is.
Okay. So you also can check, this is back to my ignorance fixation, you can also see what happens to expectation values of observables that are space-like to the coupling region. Okay, and they shouldn't know about the existence of this coupling. And you can see, again, it's an easy calculation, that these expectation values are unchanged if you update the state in a non-selective way. But under a selective update, so now I say it could have been 0 to 1 and I know it was a 0, all right? Under a selective update, these expectation values at space-like separation may change. And to start with, you think, hang on, is that maybe spooky, non-locality? Is this something we should worry about? Okay. And then you actually see, well, we actually checked, well, when is it the same? And it turns out it's the same when there is no correlation between this observable in the space-like region and the induced observable. Okay, so it is the fact that the expectation values can change is entirely attributable to correlations in the initial state. And then all of the mystery disappears. Because if you have two correlated things and you learn something about the other one, you have learned something about the other one. This is not mysterious collapse. The famous classical example of what's called Bertelsmann's socks. Bertelsmann, apparently, I think he worked at CERN and was notorious for wearing socks of different colors, okay? One red and one blue, okay? And the point is, the idea is that Bertelsmann comes into the room, you see his leg come through and there's a red sock, okay? So you already know that on the other foot, it's blue, okay? This is not superluminal communication or anything like that. It is the exercise, well, it's Bayes' rule. There's correlations here, and we learned something about one thing, therefore we may infer something about the other because we have this correlation. So that's what's happening here. Of course, in quantum theory, there are stronger correlations possible than are possible in classical theories. This is the whole Bell inequality business, and I'm not diminishing any of that, but simply this is, there is nothing particularly strange about this change in expectation values at space-like separation. But of course, knowing that there is an updated state and having a formula for it, you should worry, well, is it a good state, this update, or is it some crazy thing? So we're going to talk about that and also how you prepare states. So on this question of physical states, we want to know whether updated states have good physical properties. There is the formula again. So let's just focus on this non-selective one. You can see it's a very simple. We take a tensor product, we apply a scattering map, and then we basically take a partial trace. So the class of physical states is going to be stable under this if it's stable under tensor product, scattering maps, and partial traces. And what I did earlier this year was to investigate a class of linear theories, which includes Klein-Gordon, Procker, and more, and show that all of those properties are true for a class of Hadamard states, a slight generalization of the usual class of Hadamard states. And a consequence of that is if your system and your probe and your coupled theory are all in this class of theories, and we start with Hadamard states, so for people not so well versed in curved space-time quantum field theory, that is the nice class of states that we use for curved space-time theory, or linear theories in particular. Then the outcome is an updated state that is also Hadamard. And just to give a little detail on this, the class of operators I use is real, formally Hermitian, and green hyperbolic, which is a mouthful, so I abbreviated it by another mouthful. So I've had various reactions. One referee said that he wouldn't want to, or he or she would not want to use it as their internet password because they would forget it. And another one asked for a suggested pronunciation. So this pronunciation is that I give is RUFGO. Okay, so RUFGO is these are a nice class of operators, and I call such a thing decomposable with some cones. So these are in the cotangent bundle. They're equal and opposite cones, and they must not intersect. non-trivially. And there is associated with any rough go a certain bidistribution called Pauli-Jordan one, and the condition is that its wavefront set, which tracks its singular structure, should fall into two pieces, one of which is V plus cross V minus, and the other is V minus cross V plus. And then we have a definition of Hadamard, which is that the two-point function should have its wavefront set falling into V plus cross V minus. And that is enough to prove these properties, stability properties, that are necessary to get this stability of the of Hadamard under non-selective update. So my takeaway from that is it's a good consistency check, both of the measurement framework, but also a good consistency check on this idea of Hadamard and what is a good physical state, right? So these two things, a priori, have nothing to do with each other, work together very well in this context. So that's one recent thing. And at this point, we have a status check where we've got to, I think I have convinced you, I hope at least I've told you, whether or not you're convinced, that we can transfer information from one quantum field theory to another by these measurement schemes. And I've also told you we can gain access to local observables, well, at least approximately. So exactly is still hanging here. We still haven't said anything about state preparation. We do know something about updates. So now we move on. First, a word about statistical independence in quantum field theory. So we have Alice and Bob. They are going to be working in space-like separated laboratories, and they both wish to experiment on the same quantum field theory. Right? So you may imagine, I don't know, CERN and DAISY, and they're both doing standard model experiments or whatever it might be. Now, can they do that? Well, we know for a fact that their local algebras commute element-wise. That's by Einstein causality. So at least their observables are commensurable. So, in principle, there is some sort of, quotes, simultaneous measurability possible. However, it turns out that Alice wants to do her experiment in state omega A, but Bob wants to do his experiment in state omega B. Anybody who is a parent of more than one child has faced a dilemma like that. Anybody who has run a department or tried to run a committee or organize a conference, people have different wants and they can be very forthright about them, as we know. Okay. So you are faced with this terrible dilemma. How can we reconcile Alice and Bob? Well, Haag and Kastler had evidently had this problem somewhere in their lives, because they address it in the original paper. And they say, well, under these circumstances, what we want is that there should be a state on the system algebra which, in restriction to Alice's subalgebra, gives the expectation for Alice's state, and in Bob's subalgebra gives the expectation. Okay, so that's what Haag and Kastler say. But actually, of course, one needs more, because what we really want is for these experiments to be statistically independent. Otherwise, Alice will say, well, there's something very odd in my data here. On every Tuesday, something else happens. And that's because Bob's lazy, only goes to the lab on a Tuesday. And that's why the data gets messed up. That's not what we want. So what we really want is a statistically independent possibility for Alice and Bob to do their experiments, which means that there needs to be what we call a local product state, so that if you take a product of observables, of an Alice observable and a Bob observable, this expectation should factorize. So there are no correlations here into Alice's desired expectation on her observable and Bob's desired expectation on his observable. Okay, so this has been known, the necessity for having local product states is known, and there are nice articles by Summers and others on that going back quite some time. There are general results on when you can get a local product state. Doesn't give, as far as I can tell, a lot of control over what the state is. Maybe you get to know that it's a normal state, for example, if you start with normal states. There is a paper by Coe-Sanders which shows that there at least exist Hadamard states. Take a local product form, at least for Klein-Gordon fields in curved spacetimes, but it doesn't construct them from given states. Okay, so what I want to do is start from omega A and omega B and get this local product state. And what I'm going to do is describe a result of the following sort. If we have a quantum field theory with one of my rough goes that I like, and we've got space-like separated regions with some space safety margin, and we start with Hadamard states, omega A and omega B, then there is a Hadamard local product state of these two on the system observable. And this works in curved spacetimes.
For non-algebras or
This is actually done in the star algebra case, but then you could, I think it goes over, it'll certainly go to the C star case straight away, and I think also
normal algebra is a different story.
oh no, I think it will also work. I can't. No, it'll work. You should see the construction is very concrete. In fact, you know it quite well in some way. Okay, so this is what I want to do, and I'm going to solve the problem of exact measurement schemes in the process. And I'm going to work with the scalar field, but the idea works in greater generality. So let's take the Klein-Gordon theory, box plus m squared, and the system and probe are each going to be copies of that quantum field theory, of this thing here. So the uncoupled combination is two real scalar fields, which I may think of as being equivalent to one complex scalar field. I can do that. Now on the complex field, there is a U1 global gauge symmetry, just obtained by multiplication by phases in the field. And the trick that makes all of this work is that every one of those gauge automorphisms can be realized as a scattering map. And here's how it goes. There's space-time. We choose a smooth function, chi. It goes between 1 in the future of some slab region S to Z, which is our desired phase in the past. I have my Klein-Gordon operator E, the complex Klein-Gordon theory, but I can consider another differential operator where I just conjugate with this smooth function chi. And that gives me another second-order differential operator, which is nothing but the complex Klein-Gordon field coupled to a pure gauge external electromagnetic field, which is the gradient of chi. And outside, in particular, the gradient vanishes in the future and in the past. So it's the, you have agreement of these two operators down here and up there. So this is the theory that we work with. And if you compute the scattering map, then you find that it is exactly just this alpha of Z, global gauge transformation. And you might think about this, well, it's a pure gauge field. That's normally got no physical consequences. And of course, actually, you don't need to worry because this is a global gauge transformation. So it would leave observables unchanged, right? So that's a quick consistency check. So now we can look at what happens when we go back to thinking of it as two real fields. Well, the U1 becomes an SO2. We can compute the scattering map exactly in closed form, and here it is, using generating functions. The important thing is that if we choose S is pi by 2, you can see that the scattering map is just a flip from system into probe. And for minus pi by 2, it's a flip in the reverse direction. And that now means we can see what would happen if we used minus pi by 2 and looked at the induced observable. And there's the formula. We have a flip. We evaluate. We need to do this partial conditional expectation. We just get B. So if you look at observable B in the first place, the induced observable is just B. All right. So that solves the inverse problem because you want B, then you measure B. So that shows that the range of this induced map is certainly everything. What about a non-selective update? By the way, I'm going to criticize this. This is not going to be the end of the story in a second. If we look at non-selective update, but with plus pi by 2, we have our formula. The scattering map is a flip. When we evaluate it, we find that the non-selective update state is just the same as the probe preparation state. So if we want to prepare a given state, we just use it as the probe preparation state and perform this protocol. So we can do whatever we want, we can measure whatever we want. But all of these protocols both required control of a complete Cauchy surface. Yeah. And that is not physical, so one should not, I mean, they has a smell of something that's a bit too good to be true, and you should think of it as something a little bit too good, but we can do something about it. And here is a localization result for these measurement schemes. So let's consider two coupled variants of the uncoupled thing. We're going to have the same coupling zone, and I'm going to assume that C and C prime agree on L, which is this sort of Christmas tree arrangement in space-time. They agree on that region, and the probe preparation states agree down here in L minus, and the system states, so I can have different probe preparation states, different system states, but provided they agree down here, then you can prove that the induced observable maps for these two different coupling, the measurement schemes, agree for probe observables localized here. Okay. And the non-selective updates of these two different states resulting from two different measurement scheme couplings, they coincide here. Okay, so we can sort of localize this. This is also good because you never get to control the whole of space-time. So saying that you just need to get things right locally. So now we can go to our schemes. And instead of looking at the pure gauge guy, I just multiply it by a smooth compactly supported function that is 1 in this purple region and 0 eventually elsewhere. Chi I keep as I had for this original global measurement scheme. And then this localization result tells us immediately that the induced observable map will send probe observable B to B, not for all observables, but just for those localizable in L+. Okay, so now if you care about measuring things in L+, you know what to do. You build this Christmas tree, you run this protocol, you measure. Okay, so that is solution to this problem of can you get access to all local observables exactly? Yes, you can by this method and therefore probably other methods too. What about states? So I use the same trick. I again multiply, oh, there's something dropped off there. Again, there should be a grad psi in there. And I do the same thing. I look at the protocol with this chi that I had. The localization result tells me now that the non-selectively updated state agrees with the probe preparation state, not everywhere, but at least on L+. And whoops, in the causal complement, it has to agree with the original state because expectation values do not change in the causal complement under non-selective updates. Okay. So that's one thing. But now what about Alice and Bob? So Alice can prepare what she wants in her lab, but what about Bob? So now if we have Alice and Bob and there is a little bit of a safety margin, then they can both build a Christmas tree that remain in the causal complement of one another, or spacelight separated, and we build the Christmas trees as before, and Alice, we already know, her update gives her preparation state on that region there. And in the causal complement, so in particular where Bob's lab is, it is just the original system state omega. And then a simple calculation shows that it's a product state. You just plug it into the formula, and theta A acts trivially on Y, and it flips X into the other factor. That's what it does. It's a homomorphism, of course. So then when you evaluate this, well, you know, it's a product state for the local observable. So if omega was already Bob's preferred preparation state, that would do the job. But we can actually go one better. Suppose, I mean, because Alice and Bob wouldn't necessarily know of each other's existence. So Alice goes into her lab and she does what she's supposed to do in order to prepare, but Bob's gone into his lab and he's doing the same. All right, what happens? So this is the situation. If Bob does the same using his prepared state as his preparation state, you now use the fact that these two interactions are causally disjoint and there is a property of causal factorization, which means that the overall scattering map factorizes into an Alice scattering map and a Bob scattering map, and they act on different tensor factors, which is what that's about. Again, a calculation. Now we've got 3 algebras in the game. And so what does the scattering map do? On an Alice observable, it flips it into the second factor. On a Bob state, it flips it into the third factor. We evaluate, it's still a product state, and it's a product state of Alice's preparation state and Bob's preparation state. And because all of this has been done with non-selective updates, if everything was Hadamard in the first place, then everything we get out of this is Hadamard. So this is a construction of Hadamard local product states from Hadamard preparation states. Okay, so that is a summary of the protocol. They each make independent non-selective measurement using their desired states as a preparation state, and we get an overall local product states of what they want. And Hadamard is preserved, so would quasi-freeness, so would gauge invariance be as well. So I come to the end. Unsurprisingly, we have managed to succeed in all of our goals. And it's not surprising because I decided what the goals were going to be. And but we have complete success in these various goals here. So the overall punchline is that not only do physical local product states exist, which is known, they can be prepared. Okay, and so the world is safe for experimentalists. This is my big claim. So they should be happy. And with that, I'll thank you for your attention.
Beautiful talk.